Okay, we've now entered Chapter 6, which is all about vectors. Vectors is more for physics, but it also, I believe, has a place in, well, 3 dimensions, architecture, things like that. So far, we've just gotten used to the idea of objects on 2-dimensional space. Vectors is also going to get into objects with 3 dimensions, but right now, a vector has both a magnitude, so a length, and a direction, okay? That's what the definition of vector is. Now, as we work in 2 dimensions, we're going to be looking mostly in terms of east, north, west, and south, because that's the easiest for us to fathom. But eventually, you're going to also be working, if this was your x and y Cartesian graph, we're going to be working on an extra dimension, a 3rd dimension called z. And your vectors are also eventually going to follow this Cartesian graph. But for now, we work in 2 dimensions just to grasp it. So a lot of your SOHCAHTOA, your Pythagoras theorem, your sine law, and your cosine law are going to come in handy. So going back to exactly what a vector is, it's got both a magnitude. So let's say this goes, let's say this is a measurement of 50 meters. And we'll say that it's going northeast. Or better yet, let's just say either one works, 45 degrees from this spot. But often in the books you'll just see northeast. Now it also helps to memorize your compass. Start with north at the top, west, W is just to the left. Once you're there, south is opposite north and east is opposite west. So if you can remember this connection, you're good. If you look at this and suddenly you didn't know the distance of this vector, okay, but they told you either of these lengths down here. Let's say they told you this length was, oh, I don't know, 40 down here. Well, because you have one angle, and this is the hypotenuse in a right angle triangle, you would be able to figure out that the sine of 45, sorry, the cosine of 45 is adjacent over hypotenuse. And since we want to know that, and we know that, you rearrange this, and its hypotenuse is equal to the adjacent over the cosine of 45. We know the adjacent is 40. And we just need to figure out the cosine of 45. Now this is just a made up value, so I'm not going to get the 50 we started with. But 40 divided by the cosine of 45. And you get 56 point something, 56.56. So right there, you're able to figure out this, and you could also figure out this distance here. But you're going to need your abilities here. You're also going to have to remember some rules of shapes like parallelograms. And by definition, this angle is the same as this angle. Therefore, this object here is both parallel and the same length as that. And this object is parallel and both the same length as that. Use these double lines to match. If it had just been a single line here, I would be incorrectly saying they match that, which is possible, but it's not what I want to say in this case. You also have to get used to objects like kites, in which these objects will share a lot of the same features, especially if you're given that this angle here is the same as this angle here. That means this is the same, and it would mean that these angles are the same and that these are the same. It would also mean that this angle, let's see if that's true. Yeah, I believe this angle must match this angle, so you'd put it as double. And actually I have to do the same rules for this, because they're not all the same angles. Let's just get straight to it. So the main points of this, the review is, well, they go through the refreshers. So you have to also remember your exact values. So go back and memorize your exact values. Go back and practice your Pythagoras theorem. Here they want you to do the Pythagoras theorem. So there's the hypotenuse. So that squared is going to be equal to this squared plus this length squared. This one you'd have to use your cosine law. And over here, they walk you through the original rules for cosine and cosine and sine law, essentially. So they just want you to get refreshed on it. And then they explain to you that a vector has both a magnitude and a direction. If you don't have a direction, it's not a vector, it's just a scalar. It's just a magnitude. So if I say I'm 6 years old, that's not a direction. It's just a scalar measurement. It's just an amount, a magnitude. Vector is a mathematical quantity having both magnitude and direction. And pretty much you can create opposite vectors just by putting a minus in front and changing the arrow on the vector. So AB here is going east, and BA here is going west. And they will both have the same magnitude, just opposite directions. When you take the absolute value of either vector, you will get their magnitude, so they can share magnitude. And then they run you through on a Cartesian graph, and they also run you through the notion of equal vectors are ones that have the same direction and same magnitude, so they're parallel. And that's pretty much it. And then they run you through a couple examples. So key idea, a vector has magnitude and direction. A scalar is a mathematical quantity that only has magnitude. And then they run you through the rules of opposite directions. Okay, state whether this statement is true. If two vectors have the same magnitude, they are equal. No, they have to have the same direction as well. If two vectors are equal, then they have to have the same magnitude. That is true. Because the definition of two vectors that are equal, they have the same magnitude and same direction. If two vectors are parallel, then they are either equal or opposite vectors. No, that's not true. I can have totally longer vectors and shorter vectors that are parallel. If two vectors have the same magnitude, then they are either equal or opposite vectors. No, you can have two vectors pointing in different directions that have the same magnitude. For each of the following, state whether the quantity is a scalar or a vector and give a brief explanation why. Height, it's a scalar. There's no direction. Well, I mean up. There's an implied scalar, but no. You can measure someone's height when they're lying down. Temperature, it's a scalar. Weight, weight and mass could be defined possibly as a vector because gravity defines mass, and I believe weight doesn't matter, or vice versa. I forget. Area. That's a good one. Now, I believe that's scalar. Volume is scalar. Distance is scalar. Displacement is scalar. Speed is scalar, but velocity is not. That's the difference between speed and velocity. Speed is 50 kilometers an hour. Velocity is 50 kilometers an hour heading east. And force has to be downwards towards... No, you can apply force. No, I think force has to have a vector, because they always describe force in a specific direction. Friction is considered to be a vector because friction can be described as the force of resistance between two surfaces. Give two examples of friction of everyday life. Well, cars and snow and rain, and running. If you try to stop suddenly, you'll skid. Explain why they can be described as vectors, because they're opposite directions and they're a balanced amount. For instance, if there was no friction, you'd never be able to start or stop. You'd have to use something like a jet. You'd have to throw something in the opposite direction. That was an old space question. If you were floating in space, how would you move in this direction? Well, you have to throw an object that way. The object has a certain amount of force to it in a certain direction, and that automatically propels you that way with the same amount of force and opposite direction. Friction is very similar. When you're going this way and you hit the brakes of your car, it's your tire friction on the road that stops you, and it always requires a certain distance because the amount of friction going this way is smaller than your speed unless you're going very slow. That's why speed kills. If you go slowly, you can brake in a very short distance. If you're going way faster than the speed limit and you don't have a good distance between your next car, you're going to skid right into them every time. Doesn't matter how fast your reflexes are. Okay. Square ABC is drawn below. State four parts of equivalent vectors. I don't know if this is that relevant. Because it's a square, it's going to share a lot of things. It's going to have all the same angle and all the same length. So they're all pretty much equivalent. So DC, which is that way, is equivalent to AB. AD, which is that way, is equivalent to BC. AE will be equivalent to EC because they have all these triangles are congruent. And DE will be the same as EB, these two here. State 4 of opposite directions, okay. Let's see now. We'd have to reverse, so CD this way. Well, you just reverse all the ones we just stated. State 2 pairs of vectors whose magnitudes are equal but whose directions are perpendicular to each other. This because it's a square, and this because it's a square, and that. That's why it wasn't really worth it. If you're having trouble with that, you really have to go back and practice. Okay. Given a vector that's shown, draw a vector equal to it. Okay, so here's the easiest way to do this. Equal to it. I'm going to take my line here, pretty much map right over it, and then I'm just going to move it. So now we're parallel. And I'm going to put an arrow there, and I'm going to just give it CD. There. That's exactly equal because they're parallel, and they have the same magnitude. Opposite. Okay, I'm going to just change the arrow on it to the other end. So exactly parallel, exact same magnitude, opposite directions. Whose magnitude is equal to AB but not equal. Okay, so the secret there is you take a line like this. Now I know it has the same magnitude, but I'm just going to lower it like that. There. They have the same magnitude but different directions. Whose magnitude is twice that of AB and in the same direction. Okay, that's actually pretty easy as well. I do that, and I move it. And I do that again, and I put it on the end. It's not quite straight, and I put an arrow on it. There, that's twice as long, same direction because they're parallel. Whose magnitude is twice? Whose magnitude is half in the opposite direction? Half is a little harder to do. It's more guesswork, but it's roughly that. And then because we want the opposite direction, we do that. And helps if you label it CD. So this would be vector CD like that, telling you to go from C to D. So they're just getting you comfortable. This is a very basic physics class. You'll see it in chemistry as well. So here's your compass. It would actually help if we just took a Desmos here and we labeled every unit by steps of 1, and we took a copy of that. There we go. Okay, let's call each unit, instead of 1 centimeter, we'll call each unit 10 kilometers an hour. So he's heading due north at 40 kilometers an hour. Okay, due north, 40 kilometers an hour, all the way up to 4. Okay, and you should put a little arrow on it. Notice also that he's at 0, 4 here, and 0, 0 is his start. Car heading in the southwesterly direction at 60. That's a good point. So how would we create that 60? Well, it's a little tough to do the 60. I could actually take it to here, try to spin it around. Something like that. Another way to do it more accurately, though, is say, okay, I'm going to call southwesterly 45. Let's see. Now, I guess here we're just supposed to measure it out, so it's supposed to just be something you measure on paper, so you don't really have to do it this way. But you could roughly figure out the coordinates that you want. Since you know that you want this to be 60, let's just call it 6. We know the two sides are going to be smaller. And they're going to be equal because we're at 45. So you can call them both A, and you know that A squared plus A squared has got to equal 36. Therefore, 2A squared is equal to 36. The reason they're equal is because you went 45 degrees. Therefore, A squared is equal to 18. So that means, what's the square root of 18? 4.24. So that means you'd go about 4.24 here, 4.24 here, and you'd cross it. So this right there would be accurately 6. Okay, car traveling in the northeasterly direction at 100. So I don't have it long enough for 100. That would be 10 units. But I could roughly do it. You could also do it over here on Desmos. So again, if I want to go northeast, I know that I'm talking about 100 is equal to 2A squared. So it's going to give me the solution. What is the square root of 50? Okay, now I'm going to put 7.07 comma 7.07. I'm going to label it. All right, there it is. I think I can draw a line to it. Let's draw a line to it. So y is equal to, the slope is, I believe, going to be 1. There we go. And I've just got to restrict the range. 0 smaller than x, smaller than 7.07. There we go. So that is exactly 10 long. That's because 7 squared plus 7 squared is, that's going to come to roughly 100, and the square root of 100 is 10. So that's 10 long. A boy running in the northwesterly direction at 30. Okay, so same sort of thing. We know it's going to go a bit past 30. We know that 30 is going to be equal to 2A squared, so A is going to be the square root of 15. So if we look at 15, we know it's going to be close to 4 because 16 is 4, 3.87. So we know that this point here is 3.87 comma 3.87. It's actually minus 3.87 on this side because we're on the northwest side. So I know this length here is 3.87. If I were to draw a triangle, both sides are 3.87, and that's only because I made this exactly 45 degrees, which tells me this side and this side are the same, because they both, when you have the same angle, you're going to have the same length if the other angle is right angle. And actually the other angle has to be right angle if those are both 45. And finally, a girl running around a circular track, traveling at 15 kilometers heading due east. Okay, so here's a circular track. Put it in the middle. And if she's heading due east, she's at this point on the track. And that's assuming she's starting here. She went 3/4 of the way around. There we go. So these questions are kind of silly, but anyway, doesn't matter. The vectors shown represent the velocity of a car heading due north at 100 kilometers. Give possible interpretations of each of the vectors shown. Okay. This one is he's returning home, so he's heading south, 100 kilometers an hour. This one he's turned west. Looks to be about a third of that. So we'll say he's turned west 30 kilometers an hour. This one looks almost the same length. So he's gone 100 kilometers per hour northwest. This one looks like 1/10 of the thing. So he's suddenly gone 10 kilometers an hour northwest. This is where knowing your compass helps. So this is north and this is west. Therefore, if you go perfectly 45 degrees between the two, you're going northwest. And this is going east, looks to be about a quarter. Looks to be about 25 kilometers an hour. And actually, east looks very similar to this. So whatever unit you used here, use the same unit there. These are pretty basic questions because they can't really go too far with what they've explained so far. So describe the opposite vector. So if he's flying north, that means he's flying south at 400 kilometers an hour. If they're traveling northeast direction at 70, so remember your compass. If this is northeast, the opposite will be southwest at 70 kilometers an hour. Bicyclist is pedaling northwest, so same thing. If this is northwest, the opposite is southeast. And then you just add the amount, 30 kilometers an hour, and then a boat travels west. So the same thing with this. If this is west, then this is east, and you just add the label 25 kilometers an hour. So it's very helpful. So just remember north, and to your left is west. Once you remember those two, the rest are automatic. Okay, given a square-based prism. So the nice thing about square-based prisms is they all have right angles. And they even tell you some information. They tell you AB is 3. So right here is 3, which means this is 3, which means this is 3, which means this is 3. And they tell you AE is 8. AE is 8. Which means this is 8, which means this is 8, which means this is 8. And they state whether this is true. AB has the same vector as GH. So here's AB. Here's GH, the opposite direction. No, that is not true because it's opposite directions. EA is the same vector. The magnitude of EA is the same as the magnitude of CG. That's what these absolute value bars mean. So EA is right there, and CG is right there. Yeah, different directions, but their magnitude is the same. That's true. The magnitude of AD is the same as DC. AD, where's DC? DC. Well, that's true because they're squares, so that's the other thing I should have written down. Because it's a square prism, these sides are 3. However, if it wasn't a square prism, that would not necessarily be true. So AH is equal to BG. So we're cutting diagonally through this long face. And keep in mind all the other sides are the same. So BG. So also keep in mind it's going like that direction. And BG is the same on the opposite side. So that is true. Okay, and calculate the magnitude of BD. So we're going to go B through the bottom triangle. So we're talking about a triangle like that and like that. How do I know? because this is a square down here. Squares have right angles. This side is 3, this side is 3, and they want to go diagonally across. So that means it's going to be the square of this plus the square of this. So it's going to be the square root of 9 plus 9, which is the square root of 18. I'm not going to calculate it, but I will break it down. It's 2 times 19, which is 3 times the square root of 2, because I can bring this 9 out. I could have done it right back here instead of doing this. 3 square root of 2. What about BE? Okay, BE is going through here like that. So looking at the triangle or the side of it, we're talking 3 and 8, which means the since they don't really want compass, you can just say BE is the direction. And so you can say BE is equal to the square root of 64, which is 8 squared plus 9, which is the square root of 73. There's no real simplification of that, so that's the answer. So just put that over top of BE. And finally BH. So BH is here. Oh, here's an interesting one. So it's how do you calculate, this is the bottom left corner, this is the top right corner. How do I calculate that? Well, let's look instead at going to BD. We already calculated BD. It was 3 times the square root of 2. And then we have this straight up 8 line. So if you look at that carefully, we can see that it forms a line at the diagonal that we just measured. And it forms right angles with this 8. And this, therefore, will be the line we're looking for, B to H. We've just used the right angle triangle that happens to be diagonally through. So that means this length here is going to be the square root of 8 squared, 64, plus this squared. Well, remember that this was the square root of 18, and that squared is 18. Any square root squared is just the number inside. We've got 72 plus 10, 82, square root of 82. Can't really be simplified because there's only 4 factors, 82 and 1, 41 and 2. So this is the magnitude of BH. That's because I can form a right angle triangle between its height and the diagonal here. Let's see if I can do that a little bit more clearly. I can figure out this vector by using the diagonal from B to D along with the height from D to H. And if I look carefully, right there, that forms a right angle triangle. The base is the square root of 18. Right there, that's the square root of 18, and the height is just 8. And that green line is the hypotenuse between this and that. That sort of illustrates it a bit better. Okay, moving on. Number 10. James is running a circular track, so this is interesting. And hard to get your head around sometimes. Let's first of all analyze the track a bit. So the circular track has a circumference of a kilometer. That means all the way around it is a kilometer. Since we know that pi 2r is equal to circumference, and we know it's equal to 1, we know that the radius is equal to half 1 divided by 2 pi. So that's the radius. At any one spot, it's 1 over 2 pi. So if I'm at A, that's the distance. If I'm at B, that's the distance. If I'm at C, that's the distance. If I'm at there. So that can help me figure out some coordinates. He's going 15 kilometers an hour around that. How long would it take him to go around? Well, the distance is equal to 1 kilometer. His velocity is equal to 15. We know that velocity is equal to distance over time, and we want to figure out time. Very handy tool is a triangle like this, where you put your the numerator item at the top, then you draw it like this, and then you put this here and this here, which means velocity is equal to distance divided by time. Distance is equal to velocity times time, because they're right beside each other. Time is going to be equal to distance divided by velocity. Let's see if that's true. I bring the time over here. I get TV is equal to distance. Then I divide the velocity, and I get time is equal to distance divided by velocity. This little triangle is helpful. This thing will really help for 3 variables equations like this. Okay, so time is equal to distance over velocity. How long does it take him to go around this track? Well, we know his distance is 1 kilometer, velocity is 115. He's in kilometers per hour, so it's 1/15 of an hour. We know there's 60 minutes in an hour. 15 goes into 60, 4 minutes. So it takes him 4 minutes to go all the way around this track if he's going 15 kilometers an hour. That's useful to know. Explain why James's velocity can be represented by a vector tangent to the circle. Well, because at any point, he is changing his directions around the circle. So if you stop at any instantaneous moment, he is heading perpendicular to the track. He's adjusting minutely as he goes around, but if you look at the very instantaneous moment, it will be the tangent. And that'll be important later too. What does the length of the vector represent? The length of the vector represents his speed, 15 kilometers an hour. As he completes a lap running at a constant speed, explain why James' velocity is different at every point of the circle. Well, the magnitude's always 15, but the direction every second changes to the tangent, right? But it will have parallels at certain points, at least in magnitude. This vector up here will be the opposite of this vector down here. Same with these two vectors. And all around the circle, actually, we'll always have opposites. Determine the point on the circle where James is heading due south. That will be right here at C. He's heading due south. In running his first lap, there's a point at which James is traveling in a northeasterly direction. So northeast is that way. So here's a good way to do it. So we know that's northeast, right? And now I'm just going to move that and figure out where that would make a good tangent. It's right there. I didn't quite get my northeast right, but it's clear that at this point here is when he's heading northeast. How long does it take him to get there? Okay, let's look at where that is. We know it takes him 4 minutes to go around. So that means this is 1 minute. This is 2 minutes. This is 3 minutes. And that's halfway there. 3.5 minutes. So 3 minutes. What's a half minute? 30 seconds. Another way to look at it is if you divide this circle up like that, you get 8 pieces. You know it takes 4 minutes to do a full piece. So to do one piece takes half a minute, which is 30 seconds. So it's 30 seconds, 1 minute, 1 minute and 30, 2 minutes, 2 minutes and 30, 3 minutes, 3.5. Same answer. Okay. Determine the point of circles. Yeah, we did that. At the point he has traveled 3/8 of a lap, in what direction would James be heading? Assume he starts at A. Great, we just figured that out. So that's 1/8 right there, right? That's 2/8. Once he hits 3/8 here, he's heading in this direction. That direction happens to be southwest. So if I do reverse, so I know he hits that point there, not quite right on the tangent there. If I put it back on the compass, I can see that that is southwest. That's that. Okay, let's keep going on. And where it looks, let's see, they barely do anything in this one. It's just getting you used to what a vector is. Okay, so this we would use our Cartesian graph again. So I'm going to go to here. And I actually might even just use the actual Desmos for it. If a vector whose tail is at -4, 2, okay, let's find -4, 2 is right there. Right. And whose head is at -1, 3, okay, -1, 3 is right there. Great, we have a lot of information. Calculate the magnitude. So calculate from here to here. Well, we have a right angle triangle there. And if I draw my right angle triangle using green, I can see that this length goes from -4 to -1. That's a distance of 3. And I can see I go up from 2 to 3. So that's a distance of 1. Using my Pythagoras theorem, this length is going to be equal to the square root. This length here, magnitude, is going to be equal to the square root of 3 squared plus 1 squared, which is the square root of 10. So I could simplify it, but there's not much need. So you would just put the distance as square root of 10 because that is exact. Determine the coordinates of point D. So this is A. So this is A. And this is B. That's the other important thing. A and B. Determine the coordinates of point D on a vector CD if C is at -6 and CD is the same length, so square root of 2. So one thing we could do is, first of all, find -6, 0 right there. Draw in a green line here. And like that. That's one way to do it. But another way to do it is to say, okay, well, we know that this length is 3. So I'm going to go 1, 2, 3. And we know the height is 1. So I know it goes right here to -5, 3. And then I can just draw a line connecting those. Like that. And then don't forget your arrows. You're supposed to have an arrow on to indicate which direction you're going. And they wanted to know the coordinates of the point D. Well, we just did that. -5 because it's gone up 1. And, oh, sorry, no, I got the coordinates wrong. That's 3, -5. 3, -5. 3 because it went over 3 and it started at 0. And -5 because it went up 1. So that's the final coordinate, 3, -5. Determine the coordinates of point E for the vector E of f. If f is that, so that's the head, not the tail, and EF is the same as that. Okay, so we're now figuring out the head of this one. I'm just going to write this down in clear letters down here. This endpoint is 3, -5. Now they're giving us the head, the end of the vector, is 3 -1, -2 rather, which is here. We'll do it in blue. And we know we've got to go 3 points to the right, even though it's the opposite direction now. We know that the tail is going to be 3 points to the right, 1, 2, 3. It's going to be at 6, and 1 up right here. So it's going to be at 6 comma minus 1. Now we draw a line, and now the head is going the opposite way. So be sure to put your arrow that way. And also label it. I forgot to label the other one. The other one is C, D, and this one, the F, is over here. E. And then finally, determine the coordinates of G on the vector GH if G is 3, 1, and GH is the opposite of AB. Okay? So it's the opposite direction of AB. G is definitely the tail, so we got 3 comma 1. We'll use orange. So we got 3 comma 1. And we know that if it's the opposite direction, it's going that way, and this is definitely the tail, G, because it's the first unit. And since it goes 3, 1, 3 comma 1, we've got to go 3 that way and 1 down. So it ends at 0 comma 0. And that's how you do all of that. So it really helps to figure out your Pythagoras theorem and understand that the Pythagoras theorem is a certain amount on the x and a certain amount on the y, which is great in 2 dimensions, and it'll help you fathom 3 dimensions. And that's all there is. This will be how to add 2 vectors together to figure out where something ends up.